Andromeda sits in the night sky as a faint smear of light, and every photon of it left that galaxy 2.5 million years before you were born. When that light started its journey, no human had yet made a fire. By the time it reaches your eye tonight, an entire species will have risen, learned to speak, and built telescopes just to look back at where the light came from. That gap between when something happens and when we're allowed to know about it isn't a technicality of astronomy, it's the actual shape of space. And if it holds true for something as close as Andromeda, it may be the reason no civilization anywhere, including us, ever leaves the galaxy it was born in. In the summer of 1950, 4 physicists were walking to lunch at Los Alamos. Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York were talking about flying saucers, half joking, the way scientists sometimes do when a subject is too absurd to take seriously and too interesting to drop. The conversation moved on. They sat down. And then, according to Teller's own recollection, Fermi asked a question that had nothing to do with what anyone else was saying. He wanted to know where everybody was. He meant it literally. Fermi was doing the kind of rough calculation he was known for, the back of an envelope kind, weighing a short chain of premises that each seemed individually reasonable. The galaxy is old, something like 13 billion years by modern measurement. Stars similar to our sun are common, and a meaningful fraction of them should host planets. Given enough time and enough chances, intelligent life should arise more than once. And once a civilization can build even modest spacecraft, it has an almost unimaginable amount of time, hundreds of millions of years in some cases, to expand outward, star by star, at whatever pace it likes. Stack those premises together, and the conclusion looks unavoidable. The galaxy should already be humming with the evidence of other civilizations, or at least the wreckage and radio noise of ones that came before. So if that's true, Fermi asked, where is everybody? Not a flying saucer joke anymore. A real problem, dropped into the middle of a lunch conversation, built from premises that individually sound modest and cautious, and that together produce a conclusion nobody at that table could fully explain away. That lunch is where this video actually starts. Not because it answers Fermi's question, but because it sharpens it. 25 years later, in 1975, an astrophysicist named Michael Hart published a paper in the Quarterly Journal of the Royal Astronomical Society that tried to work the problem out properly and gave it a title almost as blunt as Fermi's original question: an explanation for the absence of extraterrestrials on Earth. Hart's math was almost uncomfortably simple. Picture a sphere of colonized space expanding outward from a single home star, growing at some fixed speed, say 1/10 the speed of light. Each new star reached becomes a new base, and after some pause, a generation or two spent building the next wave of ships, colonization continues outward from there as well. Run that model forward, and the sphere doesn't just grow, it grows at a compounding rate, the way a frontier expands faster once there are more places to expand from. Hart worked out that under this kind of model, the entire disk of the Milky Way could be crossed in something like 650,000 years. He built in generous pauses for rest and preparation between voyages, and still landed on an upper limit of about 2 million years for the whole galaxy to be reached. Set that beside the age of the Milky Way, which is measured in billions of years, roughly 13 billion by current estimates, and the travel time nearly disappears. It's the difference between a $2 million debt and a $13 billion fortune. The debt is real, but it is not the number that decides anything. So, The question Fermi asked at lunch has a kind of teeth to it. If the galaxy is old enough for this to have happened many times over, and if it hasn't happened, something is stopping it. Maybe civilizations are rare. Maybe they don't last long enough to build the ships. Or maybe, and this is the possibility this video sits with, the distances themselves are simply harder than the math on paper makes them look. Harder in a way that a clean number like 650,000 years quietly hides. Here's what I mean by that. We have actually sent something out there, so this isn't purely theoretical. Voyager 1 launched in 1977, and it is, right now, the farthest human-made object from Earth, moving through interstellar space at a little over 17 kilometers per second. That's about 38,000 miles an hour, which sounds fast, and is fast, faster than almost anything humans have ever built. At that speed, Voyager 1 is still tens of thousands of years away from even approaching the distance of the nearest star system. Not visiting it, approaching it. Proxima Centauri, the closest star to our Sun, sits about 4.2 light-years away, and Voyager, our fastest and farthest ambassador, would need on the order of 70,000 years to cover that distance if it were even pointed that way, which it isn't. Hart's model asked for something far faster, 1/10 the speed of light, which is roughly 6,000 times quicker than Voyager is moving right now. That's not a matter of better engines in the way a faster car has a better engine. As an object's speed climbs toward a real fraction of light speed, the energy needed to keep accelerating it grows faster than the speed itself does, a direct consequence of special relativity that has been tested and confirmed for over a century. In practice, that means doubling your target speed doesn't double your fuel needs, it multiplies them many times over, and carrying that fuel adds mass, which then itself needs to be accelerated and needs its own fuel in turn. This is part of why Breakthrough Starshot, a real, currently active initiative aiming to send gram-scale probes toward Alpha Centauri at around 20% of light speed, proposes pushing the spacecraft with ground-based lasers rather than carrying fuel on board at all. Carrying enough fuel to reach even 1/10 of light speed, using anything resembling current propulsion, is not just difficult. For a ship of any meaningful size, it edges toward physically impossible with technology we can presently imagine building. I remember the first time I sat with that number properly. Not the distance itself. I'd known the distance for years. The way you know a fact without really holding it. It was the speed comparison that got me. 38,000 miles an hour is genuinely fast. It's faster than a rifle bullet by a wide margin. And it still isn't fast enough to make the nearest star feel close in any human sense of the word. I had to sit with that for a minute, because it meant the problem was worse than I'd assumed. It wasn't that we hadn't built good enough rockets yet. It was that the distances themselves operate on a scale where good enough barely moves the needle. This is the quiet, unglamorous heart of what's usually called the Fermi paradox, and it's worth being precise about what it actually claims and what it doesn't. It doesn't claim we're alone. It doesn't claim intelligent life is rare, though that's one popular explanation among several. What it actually points at is a mismatch, the gap between how easy interstellar travel looks in a rough calculation on paper, at some fixed fraction of light speed, over hundreds of thousands of years, and how genuinely difficult it becomes once you try to build something that survives that journey, carries fuel for that journey, and arrives with anything intact. If this is the kind of thing that helps you drift off, it's worth subscribing. That's the only ask I'll make, and I'll make it quietly, the way I'd mention it if we were just talking. But here's the part that most explanations of the Fermi paradox leave out, and it's the actual subject of tonight's video. Hart's number, that's 650,000 years. That's the timeline for crossing one galaxy. Our galaxy. It assumes that once a civilization gets good enough at interstellar travel to hop between stars, the only thing left to do is keep hopping, star to star, outward, until the whole disk of the Milky Way has been touched. It's an assumption about ambition and patience, not really about physics. And it's usually where the conversation stops, because 100 billion stars sounds like the natural edge of any civilization's reach. Big enough that finishing the project would take almost the whole history of a species, and big enough that nobody usually bothers asking what happens after it's done. But there is an after. The Milky Way is not the edge of anything. It's one galaxy among what current surveys put at roughly 2 trillion, and if you tried to count them at a rate of 1 per second, silently, with no breaks, you would still be counting after 63,000 years had passed. All of that, scattered across a universe that is itself still expanding, and expanding faster than it used to. And when you ask what lies beyond the edge of our own galaxy, and whether anything, ever, could actually get there, the answer stops being a question of rocket engineering and starts being a question about the nature of space itself. That's a very different kind of wall than the one Hart was describing. Hart's wall was about patience and propulsion, about ships and generations, and how long a civilization is willing to wait. This new wall doesn't care how patient you are. It doesn't care how many centuries you're willing to spend on the journey, or how cleverly you solve the fuel problem, or how many gram-scale probes you're willing to launch on faith. It's built into the geometry of the universe itself, and once you understand it properly, it may be the real reason Fermi never got an answer at that lunch table in 1950. The honest answer might be that nobody gets out. Not us, not anyone, not ever. Not past a certain point. And that point, it turns out, is much closer, in cosmic terms, than almost anyone assumes. Say a civilization somewhere solves the problem entirely. Say it builds ships that survive centuries of flight, carries fuel enough for the journey, and sends out wave after wave of colonists at Hart's 1/10 of light speed, exactly as the math describes. Say it actually does what the paper predicted, and spreads star to star, patiently, for 650,000 years, until it has touched every reachable corner of its home galaxy. What has it actually won? The Milky Way is about 100,000 light-years across, measured from one edge of its disk to the other, and it holds somewhere in the neighborhood of 100 billion stars, though estimates vary depending on how you count the faintest ones. That number alone doesn't mean much until you set it beside the number from a few minutes ago, because 17 kilometers a second, Voyager's actual speed, would need something on the order of 1.8 billion years to cross that same 100,000 light-year distance, if it were even traveling in a straight line toward the far edge, instead of drifting outward the way it actually is. 1 billion years is longer than complex life has existed on land, longer than the age of most mountain ranges on Earth today, longer than nearly every geological era we have a name for. So even Hart's optimistic model, the one that gets a civilization across the whole galaxy in under 1,000,000 years, is only optimistic because it assumes speeds we have never come close to achieving with anything larger than a probe the size of a postage stamp. That postage stamp is not a figure of speech. Breakthrough Starshot, a real initiative announced in 2016 with backing that has run into the hundreds of millions of dollars, proposes exactly that. A fleet of gram-scale probes, each attached to a thin sail a few meters across, pushed by a ground-based laser array up to roughly 20% of the speed of light. At that speed, the project's own projections put a flyby of Alpha Centauri at around 20 years after launch. 25 if we're being careful about the exact figure, since different mission profiles in the published proposals land slightly differently depending on the assumed laser power. 20 years, give or take, for the near-star system, using a probe too small to carry a proper camera sensor, a full communications array, and a power source all at once without redesigning the entire concept from scratch. The current proposals solve this by keeping the probe absurdly minimal, a chip-scale spacecraft weighing about as much as a large postage stamp, carrying only the barest instruments needed to gather a handful of images and radio them home across 4 light-years of empty space. Scale that same approach up to something that could carry people, air, water, and shielding, and the laser array required grows by orders of magnitude past anything currently on an engineering roadmap. The gap between what we can send and what we could survive inside is not a small gap. It is close to the entire problem. In human terms, this is the difference between mailing a letter and moving a house. The letter can travel fast because it weighs almost nothing. The house cannot, no matter how much you want it to. There's a second cost hiding inside Hart's model that is easy to miss on first read, and it comes from relativity rather than propulsion. As an object's speed climbs toward a meaningful fraction of light speed, time itself behaves differently for the traveler than for the people left behind. This isn't speculation. It has been measured directly in 1971, when physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners and compared them afterward to clocks that had stayed on the ground at the U.S. Naval Observatory. The clocks that flew came back showing a difference of a few hundred billionths of a second. Tiny, but exactly in line with what relativity predicted, and repeatable enough that the experiment has been treated as settled physics ever since. That experiment involved a difference of millionths of a percent of light speed. Push the same underlying effect toward 20 or 30% of light speed. The range breakthrough Starshot's probes are actually designed to reach, and the difference stops being trivial. A colonist who spends what feels to them like 20 years in transit might arrive to find that 25 or 30 years have passed back home. Every subsequent wave of the colonization effort experiences its own version of this drift, so that a project meant to feel like one continuous outward push instead fractures into thousands of separate expeditions, each aging at a slightly different rate relative to the others, none of them quite synchronized with the civilization that sent them. I want to be careful here, because it would be easy to overstate this. At the speeds most real proposals actually discuss, this effect stays fairly small, a matter of years, not centuries. But stack that small effect across 650,000 years of continuous expansion, generation after generation, wave after wave, and it becomes one more way that a plan which looks clean on paper turns messy and uneven in practice. There's a third difficulty that Hart's original paper barely touches, because in 1975, the field hadn't yet worked through it in detail. What actually happens to people, biologically and socially, on a multi-generation voyage. If a ship cannot reach speeds high enough to make relativistic time dilation meaningful, and most realistic designs cannot, then a journey of centuries means a journey where nobody who leaves is still alive when the ship arrives. The travelers who reach the destination are the descendants, sometimes many generations removed, of the ones who departed. Researchers who have modeled this seriously, working through questions of genetic diversity, population size, and social stability across enclosed, isolated communities spanning centuries, generally converge on a minimum viable population somewhere in the low thousands, simply to avoid the kind of genetic bottleneck that would leave the arriving descendants too inbred to be viable. A ship built for that purpose isn't really a vehicle in any sense we're used to. It's a sealed, self-sufficient civilization in miniature, one that has to keep itself fed, healthy, and socially functional for longer than most nations in human history have lasted, with no ability to import anything from outside and no possibility of turning back. For context, that means the hardest part of reaching another star might not be the engineering at all. It might be keeping several thousand people, and their however many grandchildren, sane and cooperative in a sealed can for 300 years. There is a way to think about this whole problem that a physicist named Colin McInnes worked out formally in a framework sometimes called the light cage. Picture a growing sphere of settled space expanding outward from a single home star at some fixed rate, the way Hart imagined. Except this time the population inside that sphere is allowed to grow the way real populations do, compounding over time rather than staying flat. McInnes modeled a modest 1% annual growth rate, starting from a sphere no bigger than Earth itself, and found that under those assumptions, the expanding frontier would hit the absolute limit imposed by light speed, what he called the light cage, at a radius of around 300 light-years, reached within roughly 8,000 years of the civilization beginning to expand at all. 300 light-years sounds small next to a galaxy 100,000 light-years across, and it is small, which is exactly McInnes's point. Run the same kind of model using a more realistic maximum cruising speed, something closer to 1/10 of light speed, rather than the full speed of light itself. The range breakthrough starshot is actually targeting, and the sustainable long-term expansion rate settles down to something like 5% of light speed once you account for the time needed to rest, refuel, and regenerate a population between voyages. That number, 5% of light speed, becomes a kind of speed limit for civilizational growth itself, not because anyone chooses it, but because it's what falls out of the physics once fuel, biology, and population dynamics are all accounted for honestly. What that means in practice is straightforward, even if the math behind it isn't. A galaxy-spanning civilization doesn't get to keep accelerating its reach forever just because it keeps growing. There's a maximum rate at which any settled frontier, anywhere, made of anyone, can push outward, and that maximum is set by light speed itself, not by ambition, population, or industry. Whatever a civilization becomes, however patient or resourceful, It inherits the same speed limit every signal in the universe already obeys. So even in the most generous version of this story, the one where the fuel problem gets solved, and the ships hold together, and the colonies actually take root, star after star, the entire achievement still plays out at a tiny fraction of light speed, across a period longer than the age of most complex life on Earth, and it still only covers one galaxy. Not the neighboring one, not the thousands of others visible from any dark field on a clear night, each one holding its own 100 billion stars, its own equivalent of Alpha Centauri and Proxima, and every other close, familiar name we've given to the handful of stars near our own. One galaxy, the home one, fully explored only after an effort that would outlast the civilization's own written history many times over, assuming that history survives the effort at all. And here's where the problem actually gets larger rather than smaller. Even after every star in that galaxy has been touched, colonized, and folded into whatever the civilization has become by then, the galaxy itself is not sitting still in some fixed, waiting universe. It exists inside a much larger structure, one that is expanding, and one where the space between galaxies is not behaving the way the space between stars behaves at all. Inside a galaxy, gravity holds everything together in a fairly stable arrangement. Stars orbiting a shared center the way planets orbit a sun. Between galaxies, something else entirely is happening to the space itself. Something that has nothing to do with how fast anyone's ships can fly. The rules that govern how far a ship can travel inside a galaxy are not the same rules that govern what lies beyond its edge. That's the part almost nobody accounts for when they picture a species patiently spreading outward, star by star, until it fills the sky. The sky, it turns out, is not standing still while they work. There is a moment in the mid-1990s that most people have never heard of, even though it quietly rewrote what we thought the universe was doing. Two separate teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, working with the High Z Supernova Search Team, were both trying to measure something that sounded almost administrative: exactly how fast the universe's expansion was slowing down. Not whether it was slowing down. Everyone assumed it was, because gravity pulls things together, and a universe full of galaxies pulling on each other should be gradually losing speed, the way a ball thrown upward gradually loses speed before it falls back down. Both teams used the same tool to measure this, a particular kind of exploding star called a Type 1, a supernova, which occurs when a dead star called a white dwarf pulls in enough material from a companion star to cross a specific mass threshold and detonate, always at almost exactly the same peak brightness, no matter where in the universe it happens or how old the universe was when it occurred. That consistency makes them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from here, the difference tells you how far away it must be. The same basic principle behind judging distance from a candle's flicker at night rather than a streetlight up close. Combine that distance with how much the star's light has been stretched and reddened on its way to us, a measurement called redshift, and you can reconstruct how fast the universe was expanding at the moment that light left its source, billions of years in the past. Both teams expected to find a universe gently decelerating. Instead, working independently, Both teams found the opposite. The most distant supernovae were dimmer and therefore farther away than a decelerating universe could explain. Reese later described the reaction inside his own team as something close to disbelief, checking and rechecking the analysis on the assumption that a mistake had to be hiding somewhere in the data because the result contradicted everything the field expected going in. The two teams weren't in communication as they worked. Competitors racing toward the same measurement, which is part of why the announcement carried so much weight when both groups arrived at the same impossible-seeming conclusion within months of each other in 1998. The expansion of the universe was not slowing down. It was speeding up. That announcement landed as a genuine shock inside the field, not because anyone doubted the data once it had been checked and rechecked, but because nothing in the standard model of cosmology at the time offered an obvious reason why space itself would be accelerating apart. Whatever was causing it got a placeholder name almost immediately: dark energy, a label that describes what it does far more than what it is. To this day, nobody has a confirmed answer for what dark energy actually is at a fundamental level. That's not a gap in my research. It's a genuinely open question at the frontier of physics, and it's worth saying plainly rather than smoothing over. The 2011 Nobel Prize in Physics went to Perlmutter, Schmidt, and Reese for this discovery, a recognition of how thoroughly it reshaped the field, even though the underlying mechanism remains unexplained more than 2 decades later. What we do know is what dark energy does, and it's stranger than most people expect on first hearing it. It isn't that galaxies are flying through space away from each other, the way shrapnel flies outward from an explosion. It's that the space between galaxies is itself expanding, stretching, manufacturing more distance between 2 points without either point actually moving through space in any conventional sense. Picture 2 coins glued to the surface of a balloon. As you inflate the balloon, the coins drift apart, not because either coin is crawling across the rubber, but because the rubber between them is growing. Neither coin experiences anything like motion. The distance between them simply increases on its own. That is closer to what's actually happening between galaxies than any image involving speed or flight. And because the space itself is what's expanding, the effect compounds with distance in a way that produces something almost unbelievable if you haven't encountered it before. The more space lies between 2 points, the more of that space is expanding, so the faster those 2 points appear to separate. This is sometimes called Hubble's law, after the astronomer Edwin Hubble, who first observed in the 1920s that distant galaxies recede from us at speeds roughly proportional to their distance. The same underlying relationship that later observations of dark energy would build on and complicate. Beyond a certain distance from us, that compounding effect means galaxies are receding faster than light itself travels. I want to be precise about what that does and doesn't violate, because it's the part people usually get wrong. Nothing is moving through space faster than light. Light still obeys its speed limit everywhere, locally, exactly as relativity demands. What's happening instead is that the space those galaxies sit in is expanding fast enough that the distance between us and them grows faster than light can cross it. It's a distinction that sounds technical and turns out to matter enormously for anything we might ever hope to reach. This is where the number that changed how I think about this topic comes in. Cosmologists can calculate a boundary called the cosmological event horizon, the distance beyond which light emitted today will never reach us. Not in a million years, not in a trillion, not ever, because the space between us and that light is expanding too quickly for the light to close the gap. Based on the standard model of cosmology, with dark energy behaving the way current measurements suggest, that horizon sits at roughly 16 billion light years from Earth right now. Anything beyond it isn't just far. It is permanently, physically cut off from us in a way no future technology could ever undo, because the obstacle isn't distance in the ordinary sense. The obstacle is that the road itself is getting longer faster than anything could ever run down it. This is the part that took me the longest to actually accept, longer than almost anything else in this field, because it doesn't behave like other hard facts about space. Most cosmic limits feel like challenges, distances so vast that reaching them would require technology we don't have yet. But technology, in principle, we could imagine having someday. This one is different. It isn't a challenge waiting for a clever enough solution. It's a boundary built into the fabric of the universe itself, expanding a little further out of reach every single day. And there is no version of physics we currently understand in which that trend reverses. Here's the number that puts this boundary in perspective, and it took me longer than I'd like to admit to fully absorb it. Based on that event horizon, astronomers estimate that roughly 94% of the galaxies within our observable universe have already crossed into permanent unreachability. Not will cross, someday, given enough time. Already have. There are an estimated 2 trillion galaxies within the observable universe by current counting methods, and of the roughly 2 sextillion stars scattered across all of them, only a small fraction, on the order of 6%, sit within galaxies we could ever theoretically reach, even with a signal moving at the speed of light sent out today. If you could catalog every galaxy currently visible to our telescopes, 9 out of every 10, and then some, are already gone in every sense that matters for travel or contact, receding from us at a rate that guarantees we will never close the distance, no matter what we build, no matter how long we wait, no matter how patient or advanced we become. For context, this means the night sky is a kind of illusion, showing us light from galaxies that, by the time we're looking at them, have already drifted past the point of no return. The light still arrives, faithfully, carrying an old photograph of a place we can never actually visit. Sometimes a photograph of a place that no longer even exists in a form we'd recognize, having merged, faded, or moved on in the many millions of years since that light departed. What we're seeing when we look at most of the deep universe isn't a map of where we could someday go. It's closer to a photo album of places that have already said goodbye. And this process doesn't pause once it reaches 94%. It continues quietly every year, claiming galaxies that were still technically reachable a moment ago. Only the objects gravitationally bound to our own local group remain outside this slow erosion. The local group is a modest cluster by cosmic standards, containing somewhere around 80 known galaxies, though the real number is likely higher once fainter dwarf galaxies are accounted for, dominated by 2 large spirals, our own Milky Way and the more massive Andromeda galaxy, along with dozens of smaller satellite galaxies caught in their combined gravity. Everything inside that gravitational boundary is held together tightly enough that the expansion of space between its members is overpowered. The same way the coins glued to the balloon would stay put if you added a rubber band strong enough to hold them together despite the inflation happening everywhere else. Everything else, every galaxy not tethered to us by gravity, is being carried away on a current that never slows down and never reverses. So return for a moment to the civilization we imagined earlier, the one that spent 650,000 years patiently spreading across its home galaxy, star by star, generation by generation, exactly as Hart's model described. Even if that civilization achieves everything it set out to do, even if it fills its galaxy from edge to edge and builds a culture that spans 100 billion stars, it has still only secured a foothold inside a boundary that the universe itself is actively shrinking around every other galaxy in existence. The scale of the achievement doesn't change the scale of what remains forever out of reach. It just means the civilization has fully explored one small, temporarily accessible island in a sea that is emptying itself, one galaxy at a time, whether or not anyone is there to notice. So, if 94% of the observable universe is already gone, in the sense that matter's forever reaching it, what's left? The honest answer is smaller than most people expect, and stranger too, because the one place left standing is not empty. It has a name and a shape, and one member in particular that has been watching us as long as we've been watching it back. Andromeda is the nearest large galaxy to our own, sitting at a distance of about 2.5 million light years. That number is worth pausing on before moving further, because it means the light reaching your eyes tonight, if you looked up and found that faint smudge in a dark sky, left Andromeda when the earliest members of our own genus were only beginning to walk upright on the plains of East Africa. Every photon carries a timestamp that old. Andromeda is also not a small galaxy trailing in our shadow. It contains roughly 1 trillion stars, compared to the Milky Way's approximately 300 billion, making it the more massive of the two by a wide margin, even though the Milky Way's own dark matter halo complicates any simple comparison of total mass. And unlike almost everything else out there beyond our own local group, Andromeda is not fleeing from us. It's coming closer. We know this from its blue shift, the opposite of the red shift that tells us most galaxies are retreating. Andromeda's light is compressed rather than stretched, a signature of approach rather than departure, and it's been measured with increasing precision for over a century, since as far back as 1912, when the astronomer Vesto Slipher first recorded the telltale shift in Andromeda's spectrum, decades before anyone understood what that shift really implied about the structure of the universe. Current figures put the closing speed at around 110 kilometers per second, roughly 250,000 miles an hour, or actually closer to 246,000 if we're being precise about the conversion, fast enough to circle the entire Earth in under 2 minutes if it were moving through our atmosphere instead of the emptiness between galaxies. That is what gravity looks like operating across 2.5 million light years. Not a gentle drift, a genuine, measurable pull, strong enough to overcome the expansion of the universe itself in this one specific case. That last detail is the part worth sitting with. Everywhere else beyond the local group, the expansion of space wins, pulling galaxies apart faster and faster the farther away they sit. Here, in this one relationship, gravity wins instead, because Andromeda and the Milky Way are close enough and massive enough that their mutual attraction overwhelms the stretching of space between them. It's the same reason the coins on our inflating balloon from earlier would stay together if you added a strong enough rubber band. Andromeda is bound to us. It is, as far as current physics can tell, the one galaxy in the entire observable universe that we are not losing. For decades, the story astronomers told about this relationship was simple and dramatic. A head-on collision arriving in about 4 billion years, merging the two galaxies into one over the following 2 billion years after that. This picture solidified in 2012 when astronomers Roland van der Marel and Tony Sohn, working at the Space Telescope Science Institute in Baltimore, published a detailed analysis built on more than 7 years of patient Hubble Space Telescope observations. Their method involved tracking the almost imperceptibly slow sideways drift of individual stars within Andromeda across that 7-year span, a motion so small it required repeated, carefully calibrated imaging of the same star fields to detect at all. From that sideways motion, called proper motion, they could finally calculate not just how fast Andromeda was approaching us, which redshift and blueshift measurements had already established, but which direction it was moving sideways across the sky. The missing piece needed to predict whether the two galaxies would meet head-on or slip past each other. The result pointed toward a direct hit, and NASA described it with real confidence at the time, an event complete with visualizations showing Andromeda swelling to fill the night sky before the two galaxies tear into each other's spiral arms. But in 2025, that certainty quietly came apart. A team led by astronomer Til Sawala, using the latest data from the Gaia spacecraft and updated Hubble observations, ran more than 100,000 separate simulations of the local group's future, a technique called a Monte Carlo simulation, where each run samples slightly different values for the uncertain inputs, and the overall spread of outcomes reveals how confident any single prediction can really be. The team accounted for 22 different variables whose exact values remain uncertain: the precise mass of each galaxy, their exact current velocities, and critically, the gravitational influence of two smaller galaxies that earlier models had left out or simplified: the Triangulum Galaxy and the Large Magellanic Cloud. The result, published in the journal Nature Astronomy, was not a confirmation of the expected collision. It was closer to a coin flip. Across all the accounted uncertainty, the team found close to a 50% chance that the Milky Way and Andromeda will not merge at all within the next 10 billion years. I want to slow down on why this matters, because it would be easy to hear, the collision might not happen, and file it away as a minor correction. It isn't minor. It means that the fate of the one galaxy we are gravitationally guaranteed to remain connected to is, right now, genuinely unresolved by the best data and modeling available. Sawala's team found that including the Triangulum Galaxy's gravity makes a merger somewhat more likely, pulling the two giants together, while the Large Magellanic Cloud's orbit runs roughly perpendicular to the main Milky Way to Andromeda approach, tugging the Milky Way slightly off its collision course. These competing influences roughly cancel out, leaving a result poised almost exactly on a knife's edge between two very different long-term futures. Picture, for a moment, what each future actually looks like. In the scenario where the galaxies do collide, and there remains a real chance of a direct hit within 4 to 5 billion years, even in the newer models, the two disks pass through each other, not as solid objects crashing, but as vast, loosely packed structures of stars, separated by such enormous distances that actual stellar collisions remain vanishingly rare. The average distance between stars within a galaxy is measured in trillions of miles, so even as the overall shape of both galaxies is torn apart and eventually rebuilt into a single elliptical galaxy, some scientists have informally nicknamed Milkomeda. Individual solar systems are unlikely to be directly disturbed by a neighboring star passing close by. The more dramatic consequence sits at the center of each galaxy, where the supermassive black holes anchoring the Milky Way and Andromeda. Ours a few million times the mass of our Sun, and Andromeda's, estimated at well over 100 million solar masses, would eventually spiral toward each other over billions of years and merge in turn, releasing a final burst of gravitational waves that would be, for a brief cosmic moment, one of the most energetic events the merged galaxy had ever produced. In the other scenario, the one now carrying nearly equal odds, the two galaxies swing past each other, separated by roughly 500,000 light-years at their closest approach, 5 times the width of the Milky Way's own disk, and then drift onward, potentially orbiting each other indefinitely without ever fully merging at all. Here's what I want you to sit with for a moment, wherever you're listening from tonight. Somewhere on a hypothetical world orbiting a star inside Andromeda, if such a place exists, someone might be looking back across that same 2.5 million light years, watching our galaxy the way we watch theirs, wondering the same thing we're wondering. Are we approaching them? Are we drifting past? Neither of us can know for certain, yet, because the light we'd need to answer that question with total confidence hasn't finished making the crossing between us. We are, in a very literal sense, watching each other's past and guessing at each other's future, separated by a gap so wide that even the answer to whether we'll ever properly meet is still, quite literally, in transit. What makes this genuinely different from the story in the last section is that Andromeda represents the one piece of good news in an otherwise closing universe. It is reachable, in principle, in a way the other 94% of galaxies out there no longer are. A sufficiently patient, sufficiently advanced civilization, ours or anyone else's, could in theory eventually cross that 2.5 million light-year gap, given enough time and the right technology, because the space between here and there is not actively working against the journey the way it is almost everywhere else in the observable universe. But even here, in the one relationship spared by cosmic expansion, the future remains an open question. Reachable does not mean resolved. It only means the door hasn't been sealed shut yet. And even now, we cannot say with confidence what waits on the other side of it, or whether we are walking toward it or simply pacing alongside it in the dark. So say the coin lands on the side where the galaxies do meet. It's worth walking through what that actually looks like, slowly, because the timeline itself carries the same lesson as everything before it. Even here, in the one relationship spared by cosmic expansion, the scale of time involved dwarfs anything a civilization could plan around. The first close pass, if it happens, arrives in roughly 4 billion years. not a sudden event. The two galaxies would spend hundreds of millions of years drawing closer before that. Andromeda growing slowly larger in the sky, night after night, over a time span so long that any civilization watching it happen would need to pass the observation down across thousands of generations just to notice the shift. By the time the disks actually begin to interpenetrate, current models suggest our own sun will have already swollen into a red giant, its surface expanded past the orbit of Mercury and possibly past Earth itself, ending any possibility of terrestrial life roughly 1 billion years before the merger even begins. As the sun's growing luminosity boils away Earth's oceans and thickens its atmosphere into something closer to Venus than the world we know now. Whatever intelligence exists to watch this event, if any does, will not be us in any form we'd recognize today. It will be, at best, whatever we've become or built by then, or more likely, nothing connected to us at all, since 1 billion years is longer than the entire span of multicellular life's existence on Earth so far. The full merger, the point at which the two galaxies stop being distinguishable and settle into a single new structure, takes roughly 2 billion years beyond that first pass, putting the completed event somewhere around 6 to 7 billion years from now. Astrophysicist Avi Loeb, who co-authored some of the earliest detailed modeling of this merger, gave the resulting galaxy an informal name that has stuck in the scientific literature ever since: Milkomeda. The name is a little playful for what it describes, but it captures something true. Two galaxies that spent their entire existence as separate structures, each with its own spiral arms, its own population of stars, its own slow rotation, would cease to be two things and become one elliptical galaxy, larger than either progenitor, its stars scrambled into new orbits around a shared center, built from the wreckage of two galactic cores merging together. Because both galaxies will likely have used up most of their available gas and dust. By the time this happens, the collision won't trigger the dramatic burst of new star formation you might expect from two spirals colliding. It will be a quieter event than that, structurally violent, but visually subdued, more acetylene than an explosion. In human terms, imagine two orchestras, each playing its own symphony for billions of years, finally sharing a single hall. The individual musicians, the stars themselves, mostly keep playing their own notes. The overall shape of the music changes completely. Here's the detail that matters most for tonight's actual question though. Even in this best-case scenario, the one where our home galaxy successfully merges with its one gravitationally bound neighbor and grows into something larger and stranger, the resulting civilization, if one still exists in any form, has still only ever touched two galaxies. Not the 2 trillion, not even a meaningful fraction of the roughly 80 galaxies making up our modest local group. 2. And that merger will have taken longer to complete than complex life has existed on Earth by a wide margin, using nothing but gravity's own patient work. No propulsion required, no colonization effort, no fleet of ships. The two galaxies simply fell toward each other because they were already close enough for gravity to win. That's worth sitting with for a moment. The only intergalactic union available to us costs nothing in terms of technology and everything in terms of time. It is not an achievement a civilization plans and executes. It is something that happens to a civilization the way weather happens to a farm, on a time scale that renders any individual species' ambitions almost irrelevant to the outcome. And even this modest, passive victory has an expiration date built into the larger structure around it, because the local group itself is not the true edge of what remains reachable. It sits inside something larger, a structure astronomers call the Laniakea supercluster, a sprawling arrangement of roughly 100,000 galaxies spanning about 500 million light-years, named in 2014 by a team led by astronomer Brent Tully. Tully's group didn't map Laniakea by looking at where galaxies simply sit in space, since visual proximity can be misleading when galaxies drift at different speeds for different reasons. Instead, they tracked the actual motion of tens of thousands of individual galaxies, measuring which ones share a common gravitational flow. The way you might map a river system, not by where the water happens to be at one instant, but by tracing which direction every drop is actually moving. Wherever that flow converged toward a shared basin of attraction, they drew a boundary, and the resulting map revealed a supercluster far larger and stranger in shape than anyone had previously charted. Our own Milky Way sitting not near its center, but out toward one edge, a small suburb of a much larger metropolis nobody had properly surveyed before. Laniakea takes its name from a Hawaiian word meaning immeasurable heaven, chosen deliberately by the Discovery team to honor the scale of what they'd found. For a very long time to come, measured in tens of billions of years, the galaxies within Laniakea remain at least theoretically reachable, in the sense that light and, in principle, a sufficiently patient traveler could still cross the distances involved before cosmic expansion sealed them off entirely. But that window is not permanent. Current cosmological projections suggest that roughly 63 billion years from now, the merged descendant of our own local group, Andromeda and its neighbors, will represent the full extent of what any observer here could ever theoretically reach. Everything else within Laniakea, the great clusters known as Norma, Centaurus, Hydra, and Fornax, each containing hundreds or thousands of galaxies in their own right, will have receded beyond the cosmological horizon by then, carried away by the same expanding space that has already claimed 94% of what we can see tonight. The largest structure within Laniakea, the Virgo cluster, a gathering of more than 1,000 galaxies currently sitting about 55 million light-years away, will follow the same pattern on a longer time scale. Current projections put its departure beyond the reachability horizon at somewhere close to 100 billion years from now. Give or take, since a span that large carries real uncertainty, even in the best models, a number so large, it's almost easier to state than to actually comprehend. For context, if the entire history of the universe so far, roughly 13.8 billion years, were compressed into a single day, 100 billion years would still be more than 7 additional days stretching out beyond it, an entire week and more of cosmic time, in which nothing changes about this outcome. The Virgo cluster isn't leaving because anything is moving through space. It's leaving because the space itself keeps manufacturing more distance, patiently, uninterrupted, for longer than most of us can hold in our heads as a real span of time rather than an abstraction. So the full shape of the trap becomes visible only once every piece is in place. A civilization confined to one galaxy has, at absolute best, one plausible neighbor it might ever reach, bound to it by gravity rather than propulsion, arriving only after a merger that takes billions of years and asks nothing of the civilization at all, except to still exist when it happens. Beyond that single neighbor lies a supercluster that remains open for a while longer, tens of billions of years, before it too begins sealing itself away, cluster by cluster, following the same expanding tide that has already carried off nearly everything visible into night sky. And beyond even that supercluster lies the rest of the universe entirely. The other clusters, the other superclusters, the countless other galaxies scattered across space, already receding, already gone, in every sense that would ever let anyone actually visit them. So here is where all of this settles, if it settles anywhere. A civilization that does everything right, that solves its fuel problem and survives its own history, and spreads outward for 650,000 patient years, ends up governing one galaxy. Maybe, given billions more years and a great deal of luck in the mass and motion of its neighbors, it inherits one more, fused slowly by gravity into something larger and stranger than either galaxy was on its own. And then, no matter what it does after that, no matter how advanced it becomes or how long it endures, it watches the rest of the universe continue receding, a little more of it slipping away every year, quietly, without any drama attached to the leaving. Not because anyone failed, not because the civilization wasn't clever enough, or patient enough, or brave enough to keep going, because the space between here and everywhere else was always going to grow faster than anything could ever cross it. And that fact was true before the civilization existed, true before the stars that formed it had finished cooling from whatever nebula first gathered them, and it will remain true long after the civilization itself has gone quiet, folded back into whatever comes after a species ends. There's a particular kind of tiredness that comes with a number this large, and I don't mean that as a complaint about the topic. I mean that somewhere around the 3rd or 4th billion year figure in an evening like this, the mind simply stops being able to hold the number as a number and starts treating it as a mood instead. A general sense of vastness rather than a specific quantity you could ever actually picture. What stayed with me longer than any individual figure was something quieter than that. Not the scale of it. The scale, once you've heard enough of these figures, starts to feel almost familiar, the way a very large amount of money stops feeling real after the first few zeros. What stayed with me was accepting that this isn't a problem waiting for a solution. There's no future version of physics, as far as anyone currently understands it, in which a civilization simply tries harder and reaches the 94% that's already gone. The limit isn't a wall we haven't found the door in yet. It's closer to the shape of the room itself. And once you sit with that for a while, something in it stops feeling quite so much like a loss. Because if this is true, and the physics suggests strongly that it is, then it isn't a specific failure belonging to us. It's a condition. Somewhere else, if there's anywhere else, another civilization is very likely looking out at its own night sky, tracking its own version of an Andromeda, wondering about its own coin flip between merger and drift, watching its own 94% recede beyond a horizon it cannot cross either. Whatever they've built, however old or wise or strange they've become, they are almost certainly living inside the exact same shape of confinement we are, not trapped by any failure of ambition, trapped by the same geometry that holds all of us, everywhere, equally. There's something almost companionable in that, once you let it settle. Not comfort exactly. Comfort isn't the right word for something this large, and it would be dishonest to reach for it just because the moment calls for something gentler than the raw fact allows. But a kind of quiet solidarity across a distance that will never close, the recognition that whatever is out there, if anything is not so different from what's in here, bound to its own galaxy, reaching at best for one gravitationally patient neighbor, watching the same tide of expanding space carry away everything beyond its own small, temporarily lit corner of the dark, the way every porch light on a dark street is its own small circle, unconnected to the others, and yet somehow less lonely, simply for knowing the other circles are out there too, each holding its own small warmth against the same enormous night. The universe was never actually built for crossing. That's the quiet correction this whole subject asks of you, if you let it. We grew up on stories where distance was just an obstacle, a puzzle to be solved with enough cleverness or enough time, the kind of problem every good engineer eventually cracks if given enough centuries and enough will. But some distances aren't obstacles. They're just the actual shape of the space we live inside, the way a fish doesn't experience the ocean's edge as an obstacle so much as the boundary of what the word world even means to it. It doesn't spend its life straining against the shoreline, mourning a beach it will never walk. The shoreline simply isn't part of its question. Maybe that's closer to where this leaves us than any story about frontiers and expansion ever was. The galaxy isn't a starting point we outgrow. For every civilization that has ever existed or ever will, in whatever form, it may simply be the room. And there's a strange kind of quiet that comes with really believing that. Not defeat. Something closer to settling into a house you thought was temporary and realizing it was always going to be home, and finding, once the realization actually lands, that the house was larger and stranger and more worth living in than you'd given it credit for while you were still planning your escape from it. Fermi asked his question at that lunch table in 1950, expecting, in some sense, that a real answer existed, one that would eventually be found if enough people looked hard enough for long enough, the way a missing set of keys is somewhere, always, even when you can't see them yet. Maybe it does exist, somewhere in the details we haven't worked out yet, in the biology of how often life actually happens, or the sociology of how long civilizations actually last once they arrive, or some combination of a dozen smaller answers nobody has fully assembled yet. But maybe part of the answer was always simpler than that, sitting quietly underneath every other explanation anyone has proposed, waiting there the entire time Fermi and Hart and everyone since built increasingly careful models around it without quite naming it directly. Maybe nobody is visiting anybody, not because they don't exist, and not because they failed, but because the universe itself was never built to be crossed, not by us, not by whatever else might be listening to its own version of the same silence tonight in its own galaxy, under its own version of a sky it will never fully leave, asking, in whatever language it uses to ask such things, the same quiet question Fermi asked over lunch, and arriving, most likely, at the same quiet answer. Wherever you're listening from tonight, you're inside a galaxy. That's not a poetic way of putting it. It's the plain, literal truth of your position in space, one of a few 100 billion stars held together in a slow, ancient spin. And everything you have ever loved or lost or wondered about has happened inside this one structure, without exception, because there was never really a way for it to happen anywhere else. That was always going to be true, long before tonight, long before anyone built a telescope or asked Fermi's question over lunch. The room was fixed before any of us arrived in it. What changes, maybe, is how it feels to know that clearly. Not as a limitation pressing in from outside, but as the actual shape of the only home any of us, anywhere, will ever get to have completely. If you step outside on a clear night, low on the southern horizon in autumn, in the right conditions, you can still find that faint smudge of light that is Andromeda, unaided, with nothing but your own eyes. It will look exactly the way it has looked to every person who has ever lived and glanced upward, steady and quiet and entirely unbothered by anything happening down here. And every part of that light left its source 2.5 million years ago, traveling this entire time just to reach you at this exact moment in whatever room or car or bed you happen to be in right now. It doesn't know or care whether the galaxies will ever meet. It's simply still arriving, the way it always has, the way it will keep doing long after tonight is over, and long after anyone currently alive is here to receive it. That's the image worth keeping, more than any of the numbers. Not the 94% already gone, not the light cage, or the merger odds, or the 63 billion years until Laniakea starts closing its own doors. Just that quiet, ancient light, still showing up, still finding you, from somewhere it will most likely never let you visit. Some other night, we'll sit with a different piece of this same territory. How old the universe actually feels once you stop rounding the number. How much silence sits between one star and the next, and what that silence has always meant for anyone listening for company out there. It's the same question really, wearing a different shape each time. How large this all is, and what it means that we get to be here at all, briefly, inside it. For now, let the light keep arriving. Let the distance stay exactly what it is. You don't have to solve it tonight or ever. The universe keeps its own hours. Somewhere in it, so do you. Good night.